Tonight, we are going to take an interstellar journey. We are drifting to the next star. But here is the thing. We are not just imagining it. We are actually going to ask the question seriously. What if we left in 2026? What if we pointed a ship toward Proxima Centauri and just went? How long would it take? To answer that, we first have to understand the distance. Proxima Centauri is 4.24 light-years away. That means light itself, the fastest thing in existence, takes 4 years and 3 months to cross that gap, traveling at 300,000 kilometers every single second. Now think about that. Every second. For 4 years. That is the distance we are talking about. And we are made of matter. We cannot travel at light speed. We can barely scratch a fraction of it. The gap between what light can do and what we can do is not just large. It is the difference between a dream and a reality we are still trying to build. So how long would it actually take? That depends on what we are willing to build, what we are willing to sacrifice, and how far we are willing to push the limits of what we know. By the end of this journey, you will understand the true scale of the distance to our neighboring star, and the cost, in time and in human endurance, that such a voyage would demand. Take a moment to relax and get comfortable, and if you enjoy calm and quiet journeys into the universe like these, please support this channel by subscribing. It helps the community grow and reach more curious people. Now, let us begin. Before we can even begin to answer how long it would take, we need to truly understand what we are up against. Proxima Centauri is 4.24 light-years away. That is a number we have already mentioned. But numbers are just symbols. They do not mean anything until we translate them into something we can feel, something we can picture, something that makes our minds quietly expand. So let us try. 4.24 light-years translates to roughly 40 trillion kilometers. 40 trillion, a 4 followed by 13 zeros. It is a number so large that it has no practical meaning in our daily lives. We do not walk that far. We do not drive that far. We do not even fly that far. It belongs to the realm of imagination, until we try to actually cross it. Consider Voyager 1. Launched in 1977, it has been traveling for nearly 50 years. It moves at about 17 kilometers per second, fast enough to cross the entire Earth in less than 12 minutes. In all that time, Voyager has covered roughly 25 billion kilometers. That is the greatest distance any human creation has ever traveled. And it is barely 1/1600th of the way to Proxima Centauri. In 50 years of travel, our most distant object has covered less than 1% of 1% of the journey we are asking about. That is not a failure of engineering. It is a statement of scale. The gap between where Voyager is and where Proxima Centauri waits is so vast that it humbles everything we have achieved. And Voyager was never meant to reach another star. It was meant to explore our own solar system and then drift quietly into the unknown. If we want to reach Proxima Centauri, we need to move differently. We need to move thousands of times faster than Voyager. And that is where the real challenge begins. To feel this distance more intimately, let us anchor it in the familiar. Imagine driving a car at 100 kilometers per hour. If you started now and never stopped, it would take you approximately 5,200,000 years to reach Proxima Centauri. That is longer than the entire history of our species, longer than we have walked upright, longer than we have made fire. All of human existence is a fraction of the time it would take to drive to our nearest star. Now imagine a commercial jet at 900 kilometers per hour. 500,000 years. Civilizations would rise and fall. The pyramids would crumble to dust. And still, the star would remain impossibly distant. The space shuttle orbited Earth at 28,000 kilometers per hour. At that speed, the journey would still take over 16,000 years. That is older than agriculture, older than writing. It is a journey that would span the entirety of recorded history many times over. These speeds are impressive by human standards, but by cosmic standards, they are barely a crawl. Now consider light itself, the fastest thing in the universe. Nothing travels faster than light. And yet, even light takes 4 years and 3 months to cross the gap between here and Proxima Centauri. When you look up at the night sky and see that faint glow, you are not seeing the star as it is. You are seeing it as it was more than 4 years ago. The light that reaches your eyes tonight left that star before events that feel recent to us even happened. That is how far away it is. And if we sent a message to Proxima Centauri, it would take 4 years to arrive. A reply would take another 4 years to return. 8 years for a single exchange. The conversation would be measured in decades, not minutes. This detail will become deeply relevant when we explore the human cost of such a journey. Let us stay with the distance a little longer, because the more we understand the scale, the more we will appreciate what it takes to even try. The distance from Earth to the Sun is about 150 million kilometers. That is one astronomical unit. Proxima Centauri is roughly 265,000 astronomical units away. You could line up 265,000 Sun-Earth distances end to end, and that chain would finally reach our neighboring star. Our entire solar system, from the Sun to the outermost reaches of the Oort cloud, is only about 2 light-years in diameter. Proxima Centauri is more than twice that distance away. And it is our closest neighbor. That is the reality we are starting from, not as a limitation, as a starting point. Now we arrive at the fundamental obstacle, the reason we cannot simply build a bigger rocket and go faster. The reason interstellar travel remains so elusive despite all our ambition. The reason even our most optimistic plans are measured in centuries rather than years. It comes down to a simple equation, an equation that has governed every rocket ever launched, an equation that dictates the limits of what we can achieve with the technology we have. It is called the rocket equation, and it has a tyranny that holds us firmly in place. Let us understand what this means. A rocket moves by throwing mass backward. That is it. Every action has an equal and opposite reaction. A rocket pushes exhaust gases out of its nozzle at high speed, and the rocket moves in the opposite direction. The same principle that sends a balloon flying across the room when you release it. The same principle that propels a jet. The same principle that has governed spaceflight since its beginning. The rocket equation expresses this relationship mathematically. It tells us that the final speed of a rocket depends on 2 things: the speed at which it expels its exhaust and the ratio between its initial mass and its final mass. The initial mass includes everything: the rocket structure, the engines, the fuel, and the payload. The final mass is what remains after the fuel has been burned: the empty rocket, the engines, and the payload. Here is the problem. The required fuel mass grows exponentially with the desired speed. To double your speed, you do not need twice the fuel. You need far more than that. You need an exponential increase, and exponential growth is unforgiving. Consider this. To reach low Earth orbit, we need a speed increase of about 10 kilometers per second. The exhaust velocity of a typical chemical rocket engine is about 3 kilometers per second. Using the rocket equation, this means the initial mass of the rocket must be about 31 times the final mass. For every 1 kilogram of payload and structure, we need 30 kilograms of fuel. To reach Mars, we need about 19 kilometers per second. Now, the initial mass is about 700 times the final mass. For every 1 kilogram of payload, we need 700 kilograms of fuel. To reach the outer planets, the numbers grow even more extreme. And to reach interstellar space, to reach Proxima Centauri, the numbers become impossible. Let us put this into perspective. A rocket ready to launch into Earth orbit is 85 to 90% propellant and less than 2% useful payload. That means for every 100 kilograms of rocket on the launch pad, only 2 kilograms are actually useful. The rest is fuel that will be burned and discarded. The vast majority of what we launch is not the mission. It is the cost of the mission. And that is just to reach Earth orbit. To go further, the ratio becomes even more extreme. Consider what it would take to reach Proxima Centauri using chemical rockets alone. A manned spaceship that could reach our neighboring star, slow down upon arrival, and do it all within a single human lifetime, would need to burn an amount of fuel roughly equal to the total mass of the Sun. Our star, 1 billion times more massive than Earth. That is not a challenge. That is an impossibility. Even if we lower our ambitions, even if we accept a journey lasting tens of thousands of years, the numbers remain staggering. The Voyager probes, our fastest and most distant objects, travel at about 61,500 kilometers per hour. At that speed, they would take roughly 70,000 years to reach Proxima Centauri. 70,000 years. That is longer than human civilization has existed, longer than our ancestors first began farming, longer than we built the first cities. The entire history of human achievement, from the first settlements to the present day, would repeat itself more than 20 times over during such a journey. And remember, Voyager is a robot. It weighs less than 1 ton. A human mission would be far heavier, far slower, and far more impossible. But here is where the picture becomes interesting. The rocket equation is not just a limitation. It is also a lens through which we can appreciate our own good fortune. The escape speed from Earth is about 11 kilometers per second. The escape speed from the orbit of Earth around the Sun is about 42 kilometers per second. Both of these speeds are close to the practical limit of chemical propulsion. That means we can escape our own planet and our own solar system using the technology we have. Voyager did it. New Horizons did it. We have the capability. But this is not a universal advantage. It is a fortunate coincidence of where we live. Consider Proxima Centauri itself. It is a low-mass star, about 12% the mass of our Sun. It has a planet called Proxima b in its habitable zone, located 20 times closer to its star than Earth is to the Sun. The escape speed from Proxima b's location to interstellar space is about 65 kilometers per second, significantly higher than Earth's escape speed. This means a civilization on Proxima b would find it far more difficult to escape their solar system using chemical rockets than we do. To launch a rocket from Proxima b into interstellar space, the fuel-to-payload weight ratio would have to be larger than a few billion. Launching 1 gram of technological equipment would require a fuel tank weighing millions of kilograms, similar to the mass of the space shuttle. Launching 1 kilogram, the scale of our smallest CubeSat, would require 1,000 times more fuel than the space shuttle carried. In a way, we are fortunate. We live in the habitable zone of a bright star. Not only do we have liquid water and comfortable temperatures, but we also inhabit a platform from which we can escape into interstellar space with relative ease. Relative being the key word. The fundamental problem is not the distance. It is the fuel. If we did not have to carry our fuel with us, the journey to Proxima Centauri would be far more manageable. In theory, sending a 400-kilogram payload to Proxima Centauri, accelerating at a modest 1 gravity, reaching a maximum speed of 4/10 the speed of light, and then decelerating at the far end. This would take about 20 years. 20 years. That is a human lifetime, but it is achievable. But we cannot do that. We have to carry our fuel. And because we have to carry our fuel, every kilogram of fuel requires more fuel to move it. The tyranny of the rocket equation is not a theoretical curiosity. It is the single greatest barrier to interstellar travel. Elon Musk, the founder of SpaceX, has spoken extensively about this problem. He has described the rocket equation as one of the fundamental challenges that must be overcome to make humanity a multi-planetary species. His approach has been to focus on reusability, building rockets that can be flown multiple times, reducing the cost of access to space. But even he acknowledges that chemical rockets have fundamental limits. When asked about the possibility of reaching other stars, he has said that current systems are far from light-speed capability, and interstellar travel remains theoretical, dependent on propulsion advances well beyond today's chemical rockets. So where does this leave us? If we leave in 2026, using the technology we have today, we are not going to reach Proxima Centauri in a human lifetime. We are not going to reach it in 1,000 years. We are not going to reach it in 10,000 years. At Voyager's speed, the speed of our fastest interstellar object, it would take approximately 70,000 years to reach our neighboring star. That is not a journey. That is an epoch. Entire civilizations would rise and fall before we arrived. The languages we speak would be forgotten. The nations we know would be dust. Humanity itself might evolve into something unrecognizable. But this is not the end of the story. This is the beginning. Because we are not limited to chemical rockets. We have other technologies in development. Some are just beyond our reach. Some are speculative. Some are theoretical. And some could change everything. In the next part, we will explore what we have right now, the current state of propulsion technology, the limits we are facing, and the question of whether we can do better. So where do we actually stand today? We have established that chemical rockets are not enough. They are powerful enough to escape Earth, powerful enough to reach the outer planets, powerful enough to send small robotic probes toward the edge of our solar system. But they are not powerful enough to carry humans to another star within a human lifetime. The numbers simply do not work. But that does not mean we have nothing. It means we have to be honest about what we have, what it can do, and what it cannot. Let us start with what we have right now, the rockets that exist today. The ones that are actually flying. The ones that are launching satellites, resupplying the International Space Station, and occasionally sending robotic explorers into the deeper reaches of our solar system. The most powerful rocket ever built is the Space Launch System, developed by NASA. It stands taller than the Statue of Liberty. It produces nearly 9 million pounds of thrust at liftoff. It is designed to send astronauts to the Moon and eventually to Mars. But even this magnificent machine, the pinnacle of chemical rocket engineering, can only manage a speed increase of about 11 kilometers per second from its launch pad. That is barely enough to escape Earth's gravity and head toward the Moon. For context, to reach Proxima Centauri within a human lifetime, we would need to achieve a speed increase measured in thousands of kilometers per second. The Space Launch System, for all its power, is not even close. Then there is SpaceX's Starship, the most ambitious rocket ever conceived. Designed to be fully reusable, capable of carrying 100 tons of payload to orbit, and eventually intended to carry humans to Mars. Elon Musk has spoken about Starship as the vehicle that will make humanity multi-planetary. And in many ways, it is a revolutionary step forward. Reusability changes the economics of spaceflight. It makes access to space cheaper. It makes it more frequent. It opens doors that were previously closed. But even Starship, with all its ambition, is still a chemical rocket. It still burns fuel to push itself forward. It still carries its own propellant. It still faces the tyranny of the rocket equation. It can reach Mars, perhaps within a decade. But it cannot reach Proxima Centauri. Not in a human lifetime. Not in 1,000 years. This is not a criticism of Starship. It is a recognition of reality. Chemical rockets are the best we have. They are also the limit of what we can do with current technology. Now consider the robotic probes we have sent into the outer solar system. Voyager 1, which we have already mentioned. Voyager 2, Pioneer 10 and 11. New Horizons, which gave us our first close-up images of Pluto. These are our fastest spacecraft. These are the ones that have traveled the farthest. New Horizons, launched in 2006, reached Pluto in just under 10 years. It was traveling at about 16 kilometers per second when it passed Pluto, fast enough to cross the distance from New York to Los Angeles in less than 3 minutes. But even at that speed, it would take nearly 90,000 years to reach Proxima Centauri. 90,000 years. That is not a journey. That is a geological era. And New Horizons is small. It weighs less than 500 kilograms. It is packed with scientific instruments, but it carries no humans, no life support, no food, no water, no protection from radiation. It is a robot. And even as a robot, it cannot reach another star within any time frame that matters to us. So, what about the probes we are planning for the future? There is a concept called the Interstellar probe, proposed by NASA. It would be designed specifically to travel beyond our solar system, reaching distances of up to 1,000 astronomical units, about 10 times farther than Voyager has gone. It would use existing rocket technology and a gravity assist from Jupiter to reach speeds of about 10 kilometers per second. At that speed, it would reach the interstellar medium in about 15 years, and it would reach 1,000 astronomical units in about 50 years. That is impressive. It is also a tiny fraction of the distance to Proxima Centauri. At that speed, the interstellar probe would take over 100,000 years to reach our neighboring star. The truth is, everything we have today is built for exploring our own solar system. The distances are measured in astronomical units, not light years. The missions are measured in decades, not centuries. We are still at the beginning of our journey as a spacefaring species. But that does not mean we are stuck. It does not mean we should give up. It simply means we need to think differently. We need to look beyond chemical propulsion. We need to consider technologies that are on the horizon. There are concepts in development that could dramatically change the numbers. Nuclear thermal propulsion, for example. Instead of burning fuel to heat a gas and expel it, a nuclear rocket would use a nuclear reactor to heat hydrogen to extreme temperatures and then expel it through a nozzle. This would produce much higher exhaust velocities than chemical rockets, roughly 8 to 10 kilometers per second, compared to 3 or 4 for chemical engines. This does not sound like a huge improvement, but in the world of rocket science, even a small increase in exhaust velocity has a massive impact on the overall performance. A nuclear thermal rocket could reach Mars in about 3 months instead of 7. It could reach the outer planets in years instead of decades. It is not enough for interstellar travel, but it is a step in the right direction. Then there is nuclear electric propulsion. Instead of using heat to produce thrust, a nuclear reactor would generate electricity, which would then power an ion engine. Ion engines are incredibly efficient. They produce very little thrust, but they can run for months or even years at a time, gradually accelerating the spacecraft to very high speeds. The Dawn spacecraft, which explored the asteroid belt, used ion propulsion to travel billions of kilometers on a tiny amount of fuel. A nuclear electric system could produce similar results on a much larger scale. It could take a spacecraft to the outer planets in a fraction of the time required by chemical rockets. It could even send a robotic probe on an interstellar trajectory. But it still falls short of what we would need for a human mission to Proxima Centauri. The problem with all these technologies is the same. They are improvements, but they are not revolutions. They bring the journey time down from tens of thousands of years to thousands of years. That is progress, but it is not enough. To truly cross interstellar space within a human lifetime, we need something fundamentally different. We need concepts that go beyond what we have today. We need propulsion systems that are not limited by the physics of chemical reactions or the efficiency of ion engines. In the next part, we will explore these possibilities, technologies that exist only on paper or in the minds of engineers and scientists, concepts that could one day take us to the stars. But first, let us pause and reflect on where we are. We have built rockets that can escape Earth. We have sent robots to the edge of our solar system. We have explored planets, moons, asteroids, and comets. We have done extraordinary things with the tools we have, and yet the nearest star remains impossibly distant. That is not a failure. It is a challenge, and challenges are what drive us forward. So, we have established that chemical rockets are not enough. They can take us to the moon, to Mars, to the outer planets, but they cannot take us to the stars. Not within any time frame that makes sense for a human civilization. But we are not standing still. Engineers and scientists around the world are working on technologies that could dramatically improve our capabilities. These are not science fiction. These are concepts that are being studied, designed, and in some cases, tested. They are the next logical step in our journey beyond Earth. Let us begin with nuclear thermal propulsion. The concept is elegant in its simplicity. Instead of burning chemical fuel to produce hot gas, a nuclear thermal rocket uses a nuclear reactor to heat a propellant, typically liquid hydrogen, to extremely high temperatures. The hydrogen expands rapidly and is expelled through a nozzle, producing thrust. The advantage is significant. Chemical rockets have exhaust velocities of about 3 to 4 kilometers per second. Nuclear thermal rockets could achieve exhaust velocities of 8 to 10 kilometers per second. That does not sound like a huge difference, but in rocketry, even a modest increase in exhaust velocity translates into a dramatic improvement in performance. The rocket equation is exponential, and every improvement in exhaust velocity pays dividends. A nuclear thermal rocket could reach Mars in about 3 months, instead of 7. It could reach Jupiter in about a year instead of 5. It could reach the outer planets in years instead of decades. For missions within our solar system, this technology would be transformative. NASA has studied nuclear thermal propulsion extensively. In the 1960s and 70s, the NERVA program tested nuclear rocket engines and demonstrated their feasibility. The program was ultimately cancelled due to budget cuts and changing priorities, but the research remains relevant. Today, NASA is revisiting the concept, exploring how modern materials and manufacturing techniques could make nuclear thermal rockets safer, lighter, and more efficient. There is another variant called nuclear electric propulsion. Instead of using a reactor to directly heat propellant, a nuclear electric system uses a reactor to generate electricity. That electricity then powers an ion engine, which accelerates charged particles to extremely high speeds and expels them to produce thrust. Ion engines are incredibly efficient. The Dawn spacecraft, which explored the asteroid belt, used ion propulsion to travel billions of kilometers on a tiny amount of fuel. It produced very little thrust, but it ran continuously for years, gradually building up speed. A nuclear electric system could scale this up dramatically, providing both high efficiency and sustained power for long-duration missions. The challenge with nuclear electric propulsion is time. Ion engines produce very low thrust, so the acceleration is gradual. It takes months or even years to reach significant speeds. For missions to the outer planets, this is acceptable. For interstellar missions, it is not fast enough. Then there is the solar sail. This is perhaps the most elegant concept of all. Instead of carrying fuel, a solar sail uses the pressure of sunlight itself to propel a spacecraft. Photons from the sun strike the sail and transfer their momentum to the spacecraft, pushing it forward. The acceleration is tiny, but it is continuous. Over months and years, a solar sail can reach very high speeds. The Planetary Society, led by Bill Nye, has been a champion of this technology. Their spacecraft, LightSail, successfully demonstrated the concept in orbit. Japan's Icaros mission was the first to use a solar sail for interplanetary travel. And now there are proposals for much larger solar sails that could reach the outer planets in record time. But solar sails have a fundamental limitation. The pressure of sunlight decreases with distance from the sun. As a spacecraft moves farther away, the acceleration decreases. Beyond a certain point, solar radiation pressure is too weak to be useful. For interstellar travel, solar sails are only useful for the initial boost. They can get a spacecraft started, but they cannot carry it all the way to another star. A variation of this concept is the light sail. Instead of using sunlight, a light sail would use powerful lasers to push the spacecraft. A laser beam from Earth would be focused on the sail, providing a continuous source of thrust that does not diminish with distance. The laser could accelerate the sail to incredible speeds, perhaps reaching a significant fraction of the speed of light. This is the concept behind Breakthrough Starshot, a project funded by Yuri Milner and supported by scientists including Stephen Hawking. The idea is to send thousands of tiny spacecraft, each weighing no more than a gram, to Proxima Centauri using powerful lasers. The spacecraft would be equipped with light sails that catch the laser beam, accelerating them to speeds of about 20% the speed of light. At that speed, they would reach Proxima Centauri in just over 20 years. 20 years. That is a game changer. That is within a human lifetime. That is the kind of journey we have been imagining. But there is a catch. The spacecraft would be tiny. They would carry no humans, no life support, no cargo. They would be essentially miniature probes, each equipped with a camera and a few instruments. They would fly past Proxima Centauri at incredible speed, capturing images and data as they went. They would not stop because stopping would require as much energy as accelerating in the first place. They would simply fly past and continue on their way. For robotic exploration, Breakthrough Starshot is revolutionary. It would give us our first close-up images of a nearby planetary system within our lifetime. It would answer questions we have been asking for centuries. Are there planets around Proxima Centauri? What do they look like? Are they habitable? But for human exploration, for the dream of actually sending people to another star, Breakthrough Starshot is not the answer. It is a stepping stone. It is proof that interstellar travel is possible. It is a demonstration of what we can achieve when we think differently. But it is not the final solution. So where does that leave us? We have chemical rockets, which are not enough. We have nuclear thermal and nuclear electric, which are better, but still not enough. We have solar sails and light sails, which could send tiny probes, but not humans. We are making progress, but we are not there yet. The technologies we have discussed so far are near future. They are within our grasp. They could be developed within the next few decades with sufficient investment and political will. But they are not the technologies that will take us to the stars. For that, we need to think even bigger. We need concepts that push the boundaries of physics, concepts that seem like science fiction, but are being seriously considered by engineers and scientists. Concepts that could perhaps one day take us beyond our solar system. Now we enter the territory where science fiction begins to blur with serious scientific inquiry. These are the concepts that exist on paper, in laboratories, and in the minds of visionary engineers. They are not yet reality. They may never be. But they represent our best hope of actually reaching another star within a human lifetime. Let us begin with fusion propulsion. Fusion is the process that powers the stars. Deep within the core of our sun, hydrogen atoms are crushed together under immense pressure and temperature, fusing into helium and releasing enormous amounts of energy. It is the most efficient energy source in the universe. And if we could harness it, we could revolutionize space travel. A fusion rocket would work by creating tiny fusion reactions inside an engine, then directing the resulting plasma out of a nozzle to produce thrust. The exhaust velocities would be staggering, perhaps tens of thousands of kilometers per second. That is thousands of times faster than chemical rockets. A fusion-powered spacecraft could reach Proxima Centauri in decades, perhaps even years. The concept has been studied seriously. Project Daedalus, a study conducted by the British Interplanetary Society in the 1970s, envisioned a fusion-powered probe that could reach Barnard's star, about 6 light-years away, within 50 years. The spacecraft would be enormous, thousands of tons of fuel, a massive engine, and a relatively small payload. But the physics worked. The numbers added up. There are different approaches to fusion propulsion. Inertial confinement fusion uses lasers or particle beams to compress a small pellet of fuel, triggering a fusion reaction. Magnetic confinement fusion uses powerful magnetic fields to contain a plasma long enough for fusion to occur. Both approaches have been studied, and both face enormous engineering challenges. The biggest challenge is simply making fusion work at all. We have been trying for decades to achieve controlled fusion on Earth. The ITR project in France, one of the most ambitious scientific collaborations in history, is attempting to build a fusion reactor that produces more energy than it consumes. It has been under construction for years, and it is still years away from completion. If we cannot achieve fusion in a stationary reactor on Earth, We are a long way from building a fusion rocket that can fly. But that does not mean it is impossible. It simply means it is difficult. And difficult is not the same as impossible. Then there is antimatter propulsion. This is the most efficient energy source imaginable. When matter and antimatter come into contact, they annihilate each other, converting their entire mass into energy. The energy density is 1,000 times greater than fusion and 1,000,000 times greater than chemical reactions. A single gram of antimatter could produce the same energy as a rocket burning hundreds of tons of chemical fuel. An antimatter rocket would work by directing a stream of antimatter into a reaction chamber, where it would annihilate with ordinary matter. The resulting energy would heat a propellant which would be expelled through a nozzle to produce thrust. The exhaust velocity could approach the speed of light. A spacecraft powered by antimatter could theoretically reach Proxima Centauri in a matter of years. There is a catch. Antimatter is incredibly difficult to produce and store. We currently produce antimatter in particle accelerators, but in microscopic quantities. A single gram of antimatter would cost trillions of dollars to produce. And even if we could produce it, we would need to store it safely, keeping it isolated from ordinary matter. That requires sophisticated magnetic traps and vacuum systems. The technology is far beyond our current capabilities, but again, difficult is not the same as impossible. Antimatter propulsion is theoretically possible. It is just very, very far away. Then there is the concept of the interstellar ramjet. This is a different kind of thinking. Instead of carrying fuel, a ramjet would collect fuel from space itself. Interstellar space is not completely empty. It contains hydrogen atoms scattered throughout the galaxy. A ramjet would sweep up these atoms using a massive magnetic field, compress them, and use them as fuel for a fusion reaction. The advantage is obvious. You do not need to carry your fuel. You gather it as you go. The disadvantage is that you need to move fast enough to collect enough fuel to sustain the reaction. And the faster you go, the more fuel you can collect. But there is a problem. At relativistic speeds, the hydrogen atoms entering the ramjet would become ionized, creating drag. The drag would eventually overcome the thrust, limiting the maximum speed to about 12% of the speed of light. 12% of the speed of light. That is still incredibly fast. At that speed, the journey to Proxima Centauri would take about 35 years. That is within a human lifetime. The ramjet concept is theoretically sound, but the engineering challenges are immense. Building a magnetic field large enough to collect hydrogen across thousands of kilometers of space is far beyond our current capabilities. Now let us return to the light sail concept we introduced in the previous part. Breakthrough Starshot is the most promising interstellar mission currently being studied. The concept is simple. A powerful laser array on Earth beams energy at a tiny spacecraft equipped with a light sail. The sail reflects the light, and the momentum of the photons pushes the spacecraft forward. The acceleration is continuous, building up over time until the spacecraft reaches a significant fraction of the speed of light. The numbers are compelling. A spacecraft weighing just 1 gram, with a sail measuring about 4 meters across, could be accelerated to 20% of the speed of light within minutes. At that speed, it would reach Proxima Centauri in about 20 years. The spacecraft would be tiny, just a camera, a few sensors, and a transmitter. It would not be able to stop at Proxima Centauri. It would fly past, capturing images and data as it went, and then continue on its journey into the unknown. The challenges are immense. The laser array would need to be about 100 gigawatts, more than the total electrical power consumption of the entire planet. The sail would need to be incredibly reflective to avoid being vaporized by the laser. The spacecraft would need to transmit data back to Earth from a distance of 4.24 light-years, using a transmitter with only a few watts of power. But the project is being taken seriously. Breakthrough Starshot has received funding, and scientists are working on the technical challenges. The goal is to send the first probes to Proxima Centauri within a generation. So where does all of this leave us? We have explored chemical rockets, nuclear thermal propulsion, nuclear electric propulsion, solar sails, light sails, fusion propulsion, antimatter propulsion, and interstellar ramjets. Some of these technologies are within reach. Some are far beyond us. Some may never be possible. But one thing is clear. Interstellar travel is not impossible. It is simply difficult. And the more we learn, the more we realize that the barriers are engineering challenges, not fundamental laws of physics. This naturally leads to an even deeper question. What happens when we actually start moving at these speeds? What happens to time itself? The faster we go, the stranger the universe becomes. Now we enter one of the most fascinating aspects of interstellar travel, something that changes everything we have discussed so far. Something that makes the question, how long would it take, far more complicated than it first appears. We have been talking about speed, about kilometers per second, about fractions of the speed of light, about getting from here to Proxima Centauri in decades or years. But there is a catch, a profound catch that most people do not consider. Time does not behave the way we think it does. This is not philosophy. This is physics. This is one of the most well-tested and confirmed theories in all of science. Albert Einstein gave us the theory of special relativity in 1905, and it fundamentally changed our understanding of the universe. One of its most startling predictions is that time moves differently for objects moving at different speeds. The faster you move, the slower time passes for you relative to someone who is stationary. This is called time dilation, and it is not a theory. It is a fact. It has been measured. It has been confirmed. It happens every day. GPS satellites have to account for it, or their clocks would drift out of sync, and the system would fail within hours. Particles accelerated to near light speed in laboratories decay more slowly than they should. The universe itself behaves exactly as Einstein predicted. So what does this mean for our journey to Proxima Centauri? It means that the answer to how long would it take depends entirely on who is asking the question. Are we measuring time on Earth, or are we measuring time on board the ship? The two are not the same. Let us work through this carefully. Imagine we build a spacecraft that can travel at 80% of the speed of light. At that speed, the journey to Proxima Centauri, as measured from Earth, would take about 5.3 years. 4.24 light-years divided by 0.8 light-years per year gives us 5.3 years. That is straightforward. But here is where things get strange. For the people on board the ship, time would pass more slowly. At 80% of the speed of light, the time dilation factor is about 1.66. That means for every year that passes on Earth, only about 218 days pass on the ship. The journey that takes 5.3 years from Earth's perspective would feel like only about 3 years and 2 months to the travelers. 3 years and 2 months. That is a significant difference. The crew would age 3 years, while everyone on Earth would age 5 years. They would return to a world that had moved on without them. Now let us push the speed further. Imagine we can travel at 95% of the speed of light. The time dilation factor increases to about 3.2. The journey, as measured from Earth, would take about 4.4 years, but on board the ship, only about 1.4 years would pass. Less than a year and a half. At 99% of the speed of light, the time dilation factor is about 7. The journey from Earth's perspective would take about 4.3 years. But on board the ship, only about 224 days would pass. Less than 8 months. At 99.9% of the speed of light, the factor is about 22. The journey from Earth's perspective would still be about 4.3 years, but on board the ship, only about 71 days would pass. At 99.99%, the factor is about 71. The onboard time would be just over 20 days. At 99.999%, the factor is about 223. The onboard time would be just about 7 days. Do you see where this is going? As we approach the speed of light, the journey time from Earth's perspective approaches 4.24 years. That is the time it takes for light to cross the distance. But the journey time on board the ship approaches 0. The faster we go, the shorter the journey feels to the travelers. If we could reach the speed of light itself, the journey would be instantaneous. Light does not experience time. For a photon, traveling from Proxima Centauri to Earth takes no time at all. It is born, it travels, and it arrives, all in the same moment, from its own perspective. This is one of the most mind-bending aspects of relativity. The faster we go, the more the universe bends to our will. Distance contracts. Time dilates. The journey becomes shorter and shorter, not because the distance changes, but because time itself changes. Now let us consider what this means for a human mission. Imagine a crew leaves Earth in the year 2026, traveling at 99% of the speed of light. From Earth's perspective, the journey to Proxima Centauri takes about 4.3 years. That means they arrive in the year 2030. From the crew's perspective, the journey takes about 224 days, less than 8 months. They arrive having aged less than a year. But here is the thing. They cannot go back. They cannot easily return. The distance from Earth to Proxima Centauri is the same in both directions. If they turn around and come home, the journey from Earth's perspective takes another 4.3 years. They would arrive back on Earth in the year 2034. But on board the ship, the return journey takes another 224 days. The crew would have aged about 18 months total. But everyone on Earth would have aged about 8 years and 7 months. The crew would return to a world that had moved on. Friends would be older. Family members might be gone. The society they left would have changed. They would be strangers in their own time. Now imagine a more extreme scenario. Suppose we build a spacecraft that can reach 99.99% of the speed of light. The time dilation factor is about 71. A journey to Proxima Centauri would take about 4.3 years from Earth's perspective, but only about 20 days from the crew's perspective. 20 days. That is less than a month. The crew would leave Earth, spend 3 weeks on board the ship, and arrive at Proxima Centauri. They would have aged less than a month. But on Earth, more than 4 years would have passed. And imagine if they stayed at Proxima Centauri for a few years, exploring the planet, collecting data, and then returned. By the time they arrived back on Earth, decades would have passed. The people they knew would be old. the world they remembered would be gone. This is sometimes called the twin paradox. Imagine two twins. One stays on Earth. The other takes a journey through space at near light speed. When the traveling twin returns, they are younger than the twin who stayed behind. It is not an illusion. It is not a trick. It is physics. The traveling twin has literally aged less. This has profound implications for interstellar travel. It means that journeys to other stars are not just about distance. They are about time, about how time is experienced differently depending on where you are and how fast you are moving. For a crew traveling to Proxima Centauri, the journey could feel like months or even weeks, depending on how fast they are willing to go. But for everyone else, for the people left behind on Earth, the journey takes years. The crew returns to a world that has moved on. They return as time travelers in a sense. Not traveling through space, but through time, moving forward at a different rate than everyone else. This raises an interesting question. Is it worth it? Is it worth leaving everything behind, knowing that you will return to a world that is different? Knowing that you will have aged less than everyone you left behind? Knowing that your children might be older than you? Some people would say yes. Some people would say the chance to explore another world, to see another star up close, is worth any sacrifice. Others would say no. Others would say the cost is too high. And that leads us to an even deeper question. What about the people who do not return? What about the ones who travel to Proxima Centauri and decide to stay? What about the ones who build a new civilization on a distant world, knowing that they will never see Earth again? This is not just science fiction. This is real. If we ever send humans to another star, we are sending them on a journey that will change their relationship to time itself. They will leave one world and arrive at another, having aged only a few years, but having left behind a world that has aged many more. The cost of interstellar travel is not just measured in fuel and engineering. It is measured in human terms, in relationships, in connections, in the very fabric of what it means to be human. This is what we call the human problem, and it is perhaps the most difficult challenge of all. We have talked about distances that boggle the mind. We have talked about speeds that push the limits of physics. We have talked about time itself bending and stretching in ways that seem like magic. But now, we arrive at something even more fundamental, something that no amount of engineering can solve, something that no propulsion system can overcome: the human problem. Because at the end of all our calculations, at the end of all our theories and concepts and revolutionary ideas, we are still talking about people. Human beings, fragile, complicated, deeply social creatures who were never designed for the emptiness of interstellar space. Let us begin with the biological reality. The human body evolved on Earth. It evolved under the protection of our planet's magnetic field, which shields us from the harsh radiation of space. It evolved under the constant pull of gravity, which shapes our bones, our muscles, our circulatory systems. It evolved to breathe air, to drink water, to eat food grown in soil under the light of our sun. Space provides none of these things. Beyond Earth's protective magnetosphere, radiation is everywhere. Cosmic rays from distant supernovae, solar particles from our own star, galactic radiation that penetrates everything. The human body is not equipped to handle this. Radiation damages cells. It breaks DNA strands. It increases the risk of cancer. It can cause cataracts, cardiovascular disease, and damage to the central nervous system. We have measured the radiation levels on the International Space Station. Astronauts there receive about the equivalent of 8 chest X-rays per week. That is acceptable for a 6-month mission. But for a journey lasting years or decades, the cumulative dose would be catastrophic. Without extensive shielding, the crew would be exposed to levels of radiation that would exceed NASA's lifetime limits within a matter of months. Shielding is not a simple solution. To block cosmic radiation effectively, you need mass. Large amounts of mass. Water tanks, lead walls, or other dense materials. But adding mass to a spacecraft makes it heavier, and making it heavier makes it harder to accelerate. The tyranny of the rocket equation returns, demanding fuel for every kilogram of shielding. We can mitigate the risk. We can design spacecraft with radiation shelters. We can use active shielding with magnetic fields. We can choose travel routes that minimize exposure. But we cannot eliminate the risk entirely. The crew of an interstellar mission would be exposed to radiation levels that are orders of magnitude higher than anything we have experienced in spaceflight to date. Then there is the problem of gravity. The human body is designed for gravity. Without it, our bones lose density. Our muscles atrophy. Our blood pools in our upper bodies. Our immune systems weaken. We have seen this on the International Space Station. Astronauts lose bone mass at a rate of about 1% per month in microgravity. After a year in space, they can lose up to 20% of their bone density. That is equivalent to the bone loss experienced by an elderly person with severe osteoporosis. We have countermeasures, exercise, resistance training, specialized diets, but these are only partially effective. After a long-duration mission, astronauts struggle to walk. They need weeks or months of rehabilitation to recover. And that is after just a year in space. Imagine a journey lasting years or decades. The human body would not survive. It would not simply adjust. It would break down. The muscle loss, the bone loss, the cardiovascular changes, the immune dysfunction, all of these would accumulate over time. The crew would arrive at their destination weak, fragile, and potentially incapacitated. We could create artificial gravity. A rotating spacecraft could simulate gravity through centrifugal force. The concept is elegant, but the engineering is complex. A spacecraft large enough to rotate comfortably would need to be massive. It would need to be strong enough to withstand the stresses of rotation. It would need to be designed so that the crew can live and work in the rotating sections. It is possible, but it adds enormous complexity to an already difficult mission. Now consider the psychological toll. Imagine leaving Earth. Imagine watching your home planet shrink to a point of light and then disappear entirely. Imagine knowing that you will never see it again. Imagine knowing that the people you love, the places you know, the world you grew up in, are gone forever. This is not just a journey. It is a separation. A permanent, irreversible separation. The crew of an interstellar mission would be leaving everything behind. Not for a few years, not for a decade, but forever. They would never return to Earth. They would never see their families again. They would never walk on grass, feel rain on their skin, breathe unfiltered air. This is the psychological weight that every interstellar traveler would carry. And it is heavy. Consider the isolation, the loneliness. The crew would be confined to a small spacecraft for years or decades. They would have no privacy, no escape. They would see the same faces, hear the same voices, eat the same food, perform the same routines, day after day after day. We have studied isolation on Earth. The Biosphere 2 experiment in the 1990s isolated a group of people for 2 years. It was a disaster. The crew fractured. They became hostile. They formed factions. They refused to speak to each other. And that was on Earth, with sunlight and plants and a connection to the outside world. Mars missions, which would last about 2.5 years, would push the limits of human psychology. Studies have shown that even well-trained astronauts can experience depression, anxiety, and interpersonal conflict during long-duration missions. The crew of an interstellar mission would be subjected to these pressures for much, much longer. And there is no escape, no abort button, no emergency return. If a crew member becomes unstable, if they become a danger to themselves or others, there is no help. There is no rescue. There is only the ship, the void, and the silent stars. This raises a profound ethical question. Do we have the right to send people on such a journey? Do we have the right to ask them to sacrifice everything? Do we have the right to expose them to radiation, to isolation, to the crushing weight of forever? Some would argue that we do. Some would argue that the chance to explore another world, to build a new civilization, to carry humanity to the stars, is worth any sacrifice. Some would argue that there will always be volunteers, people willing to give up everything for the dream of reaching another star. But it is not that simple. The ethical considerations are not just about the initial choice to volunteer. They are about the entire journey, about what happens when the reality sets in, about what happens when the crew realizes that they cannot go back, about what happens when the isolation becomes unbearable. We have not solved these problems. We have barely begun to understand them. The psychological challenges of interstellar travel are as daunting as the engineering challenges. Then there is the problem of generations. If we cannot achieve speeds that allow a journey within a single human lifetime, we have another option: a generational ship, a spacecraft large enough to sustain a population for hundreds or thousands of years, a mobile world, carrying humanity across the void. The concept is both beautiful and terrifying. A generational ship would be a self-contained ecosystem. It would have to produce its own food, recycle its own water, maintain its own atmosphere. It would have to be a functioning society, with its own government, its own culture, its own way of life. The crew of a generational ship would not be the ones who arrived at Proxima Centauri. Their children would not be the ones who arrived, nor their grandchildren. The journey would take so long that dozens, hundreds, or thousands of generations would live and die on board the ship. Think about what that means. The people who start the journey would never see its completion. They would be making a sacrifice, not for themselves, but for their descendants. For people they would never meet. For a future they would never experience. This raises even deeper ethical questions. Do we have the right to impose such a life on future generations? Do we have the right to trap people inside a spacecraft, forcing them to live and die without ever setting foot on a planet? Is it ethical to create a society whose sole purpose is to continue a journey that none of them chose? These are not easy questions. They are not science fiction. They are real. They are the questions that we would have to answer if we ever decide to build a generational ship. There is another possibility: suspended animation, cryogenic sleep, hibernation. If we could put the crew into a state of suspended animation, they would not age. They would not need food or water. They would not suffer the psychological effects of isolation. They would sleep through the journey, waking up decades or centuries later at their destination. The concept is common in science fiction, but the reality is far more difficult. We have induced hypothermia in animals, extending their lifespan for short periods. But we have not achieved true suspended animation. We do not know if it is possible. We do not know if human cells can survive prolonged periods of near-freezing temperatures. We do not know if the brain can be revived after years of dormancy. Even if we solve the technical challenges, the ethical questions remain. Is it acceptable to place people in suspended animation without their consent? Can they give informed consent if they do not fully understand the risks? What happens if the revival process fails? What happens if the crew wakes up to find that something has gone wrong? These are not hypothetical questions. They are the questions that would confront any serious attempt at interstellar travel. Now consider the social dynamics of such a journey, a group of people confined together for years or decades. No escape, no privacy, no relief from each other. This is the recipe for conflict. We have seen it in isolated communities on Earth, in polar research stations, in submarine crews, in long-duration space missions. The psychology of isolation is well studied, and the results are not encouraging. People need purpose. They need meaning. They need connection to something larger than themselves. On a generational ship, those needs would be magnified. The crew would need a sense of purpose that extends beyond survival. They would need a reason to continue, a reason to endure. Perhaps that purpose is the destination itself. Perhaps it is the knowledge that their sacrifice will lead to something greater. Perhaps it is the hope that their descendants will see the stars. But hope can only carry you so far. The reality of the journey would be crushing. The emptiness, the silence, the endless repetition of days that blur into years that blur into decades. The knowledge that you are drifting through the void, utterly alone, utterly insignificant, waiting for a destination that will never come in your lifetime. This is the human problem, and it is not solved by better engines or faster speeds. It is solved by understanding what it means to be human, by understanding our limits, our strengths, our capacity for sacrifice and endurance, by understanding that a journey to the stars is not just a technological challenge. It is a human challenge. We have talked about the distance. We have talked about the speed. We have talked about time dilation and the human body and the psychological weight of leaving everything behind. But there is another dimension to this journey that we have not yet explored, something that touches on the very nature of what it means to be human, something that makes the isolation of interstellar travel even more profound: communication. In our daily lives, we take communication for granted. We pick up a phone and speak to someone on the other side of the planet. We send a message, and it arrives instantly. We watch events unfold in real time, no matter where they happen. The world is connected. The world is immediate. Interstellar space is not like that. The distance to Proxima Centauri is 4.24 light-years. That means light, the fastest thing in the universe, takes 4 years and 3 months to cross that gap. And communication, like everything else, is limited by the speed of light. Think about what that means. If we send a message from Earth to a spacecraft heading toward Proxima Centauri, that message will take over 4 years to reach the ship. And any reply from the ship will take another 4 years to return to Earth. That means a single exchange, a question and an answer, would take more than 8 years. 8 years for a conversation. A simple back and forth that would take seconds on Earth would span nearly a decade in interstellar space. Imagine what that would feel like. Imagine sending a message to someone you love, knowing that you will not receive a reply for 8 years. Imagine waiting 8 years for a simple reassurance, a simple acknowledgement, a simple word of comfort. Imagine the loneliness of that wait. Now consider the implications for mission control. On every space mission in history, astronauts have been in constant contact with Earth. They can ask questions. They can receive guidance. They can be reassured by the voices of people who care about them. The communication delay to the Moon is about 1.5 seconds. To Mars, it is between 4 and 24 minutes, depending on the planet's positions. That is manageable. You can have a conversation, albeit with a slight delay. But to Proxima Centauri, the delay is measured in years. 4 years. That is not a conversation. That is a monologue. The crew would send a message, and then they would wait, and wait, and wait. 4 years for a response. 4 years of silence. Think about what that does to the human psyche. We are social creatures. We need connection. We need validation. We need to know that we are not alone. Without real-time communication, the crew would be cut off from everything they have ever known. They would be isolated in a way that no human has ever experienced. Consider the emotional weight of this. Imagine you are on the ship. You have just arrived at Proxima Centauri. You have spent years traveling, enduring the hardships of spaceflight. You have finally reached your destination. You want to share this moment with someone. You want to tell someone what you have seen. You send a message to Earth, and then you wait. You wait 4 years for your message to arrive. You wait another 4 years for a reply. By the time you receive the response, you have been at Proxima Centauri for 8 years. The excitement of arrival has faded. The moment you wanted to share is long past. The people on Earth have moved on. They have lived their lives. They have changed. And you are still here, waiting for a reply that took 8 years to arrive. This is not just about communication. This is about connection. About the fundamental human need to share our experiences with others. About the loneliness of experiencing something extraordinary without anyone to share it with. Now consider the broader implications. Suppose the crew encounters something unexpected. A technical malfunction. A medical emergency. A discovery that changes everything. They cannot call for help. They cannot ask for advice. They must solve the problem themselves, with no input from anyone else. They are completely on their own. This is what it means to be an interstellar traveler. You are self-sufficient. You are independent. You are also utterly alone. There is no help. There is no rescue. There is only the ship and the void and the silent stars. And the communication delay is not just a problem for the crew. It is a problem for everyone on Earth. Imagine waiting 4 years to hear from the explorers you sent to another star. Imagine waiting 4 years for a message that might never come. Imagine the uncertainty, the anxiety, the fear. This is the reality of interstellar exploration. It is not a quick trip. It is not a simple adventure. It is a commitment that spans decades. A commitment that tests the patience of an entire civilization. Now, let us consider what communication would actually look like. Sending a message across interstellar space is not easy. It requires powerful transmitters. It requires large antennas. It requires careful aiming. The signal weakens with distance, spreading out across the vast emptiness of space. By the time it reaches Earth, it is barely a whisper. The Voyager probes, which are about 1/1600th of the distance to Proxima Centauri, transmit at a power of about 20 watts. That is about as powerful as a refrigerator light bulb. By the time the signal reaches Earth, it is incredibly faint. Detecting it requires massive antennas like those of the Deep Space Network. Now imagine transmitting from Proxima Centauri. The distance is more than 1,600 times greater. The signal would be 1,600 times weaker. Detecting it would require unimaginably sensitive receivers. It would require careful planning. It would require patience. And what about the content of the messages? A simple text message would take 4 years to arrive. A high-definition image would take much longer. A video would be almost impossible. The crew would have to choose their words carefully. Every message would be precious. Every word would carry weight. Now consider the psychological effect of this on the people back on Earth. Imagine waiting 4 years to hear from your loved ones. Imagine waiting 4 years to find out if they are still alive. Imagine waiting 4 years for a message that might never come. This is the emotional reality of interstellar travel. It is not just about technology. It is about relationships, about connection, about the bonds that hold us together across the vast emptiness of space. And it is not just about the crew. It is about everyone left behind. The families, the friends, the communities. They have no control. They can only wait. Wait for a message that takes 4 years to arrive. Wait for news that is already 4 years old. This is a strange kind of relationship. A relationship measured in years. A relationship where the people involved are constantly out of sync. The crew experiences time differently than the people on Earth. They age slower. They feel time pass differently. They return to a world that has moved on without them. We touched on this in the previous part when we discussed time dilation. But now we can feel it more viscerally. The communication delay is not just a technical problem. It is a human problem. It is a problem of connection and isolation and the very nature of what it means to be human. And it is not just about the crew. It is about the future of human civilization. If we ever establish a colony on Proxima Centauri, that colony would be isolated. It would have no real-time communication with Earth. It would have to be self-sufficient. It would have to be independent. The people of that colony would grow up knowing that they are cut off from their home world. They would know that their messages take 4 years to arrive. They would know that they are alone in a way that no human has ever been alone. This raises a profound question. Is it worth it? Is it worth the isolation, the loneliness, the emotional cost? Is it worth building a civilization on a distant world, knowing that it will forever be cut off from its origins? Some would say yes. Some would say that the chance to expand humanity beyond Earth is worth any cost. Some would say that the isolation is a small price to pay for the opportunity to explore the stars. But it is not a small price. It is a profound price. A price that we are only beginning to understand. Consider the cultural implications. A colony on Proxima Centauri would develop its own culture, its own language, its own way of life. It would be shaped by its isolation, by its distance from Earth, by the unique challenges of its environment. Over time, it would become something different, something new, something that might not even recognize its origins. This is not science fiction. This is history. Throughout human history, isolated communities have developed unique cultures, unique languages, unique identities. The distance between Earth and Proxima Centauri would be far greater than any distance that has ever separated human communities. The isolation would be complete. The separation would be total. And what about the relationship between Earth and the colony? Without real-time communication, without the ability to share experiences and events as they happen, the connection would fade. The colony would become a distant memory, a legend, a story told to children. This is the deeper meaning of the communication problem. It is not just about sending messages, it is about the nature of connection, about what holds us together as a species, about the bonds that transcend distance and time. And it is something we have to consider seriously if we ever decide to send humans to another star. After all of this, After the distance, after the speed, after the time dilation, after the human cost, after the isolation, after everything, we finally arrive. Proxima Centauri. The star itself is modest. It is what astronomers call a red dwarf. It is about 12% the mass of our Sun. It is much cooler, much dimmer, much smaller. It shines with a faint reddish glow, barely visible to the naked eye from Earth. In the night sky, it is just another point of light among billions. But this star is special, because around it orbits a planet that has captured our imagination, a planet that might, just might, be a second home for humanity. Its name is Proxima b. Discovered in 2016 by astronomers using the European Southern Observatory's HARPES instrument, Proxima b is an Earth-sized world orbiting within the habitable zone of its star. The habitable zone is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold, just right. Proxima b is about 1.27 times the mass of Earth. It orbits its star at a distance of about 7 million kilometers. That is incredibly close, about 20 times closer than Earth is to the Sun. But because Proxima Centauri is so dim, that close orbit places the planet squarely in the habitable zone. A year on Proxima b lasts just 11.2 Earth days. 11 days to orbit its star. Imagine that. Your birthday would come around 33 times a year. The seasons would change in a matter of days. The rhythm of life would be radically different from anything we know on Earth. But there is a catch. Proxima b is tidally locked to its star. That means the same side of the planet always faces the star, just as the same side of the Moon always faces Earth. One side is in permanent daylight. The other is in permanent darkness. This creates a stark world. The day side would be bathed in the faint red light of its star. The night side would be perpetually dark and frozen. Between them, along the terminator, there might be a narrow band where temperatures are moderate, a twilight zone where liquid water could exist, a place where life, if it exists, might cling to existence. The conditions on Proxima b are not ideal. The star is a flare star, prone to violent outbursts of radiation. These flares could strip away the planet's atmosphere. They could bathe the surface in deadly radiation. They could make the planet uninhabitable for life as we know it. We do not know if Proxima b has an atmosphere. We do not know if it has liquid water. We do not know if it has a magnetic field to protect against radiation. We do not know if it is truly habitable. We know almost nothing. What we know is that the planet is there, and that it is roughly the size of Earth, and that it orbits within the habitable zone of its star. Everything else is speculation. But that is not the point. The point is that this planet exists. It is real. It is out there. And it is the closest thing we have to a second home. Now imagine arriving at Proxima b after all those years of travel. Imagine the moment when the planet comes into view. A small, rocky world bathed in the faint red light of its star. A world that no human has ever seen. A world that holds the potential for everything we have dreamed of. The crew would not know what to expect. They would have spent years traveling, years waiting, years preparing for this moment. And now they are here. The first humans to reach another star. The first humans to orbit another world. What would they see? What would they find? If Proxima b has an atmosphere, it might be visible from orbit. A thin haze of gases surrounding the planet. Perhaps clouds. Perhaps weather. Perhaps something familiar. Perhaps something completely alien. If Proxima b has water, they might see oceans. Not blue like Earth's oceans, but perhaps a different color, reflecting the faint red light of the star. Reddish oceans. Alien oceans. Oceans that have never been touched by human hands. If Proxima b has life, they might detect it from orbit. Signs of biology. Patterns in the atmosphere that could not be explained by geology alone. The first evidence of life beyond Earth. The most profound discovery in human history. But they might find nothing. A barren world, a frozen desert, a dead planet, stripped of its atmosphere by the stellar flares of its temperamental star. A world that looks like home, but is utterly lifeless. This is the uncertainty that the crew would face. The hope, the fear, the anticipation, the knowledge that they have traveled for years to reach this moment, and that everything they find will be worth it, regardless of what they discover. Because the journey itself is meaningful. The act of reaching another star is meaningful. The knowledge that humans can travel beyond their solar system is meaningful. And this is where we arrive at the deeper question. The question that has been quietly building throughout our journey. Why are we doing this? Why do we want to reach another star? Why do we dream of distant worlds? Why do we sacrifice everything for the chance to explore? The answer is not simple. It is woven into the fabric of who we are. It is part of our nature, our restless curiosity, our need to explore, our desire to understand. We have always looked to the stars. Our ancestors looked up at the night sky and wondered what was out there. They told stories about the stars. They named them. They used them to navigate. They dreamed of reaching them. We are no different. We still look up. We still wonder. We still dream. The only difference is that we now have the technology to turn our dreams into reality. And that brings us to the final part of our journey. The deeper question, the one that ties everything together, the one that gives meaning to all of this. Why do we want to reach Proxima Centauri? And what does it say about us? We have traveled far. Farther than any human has ever gone, even if only in our imagination. We have crossed distances measured in light years. We have pushed the limits of physics. We have confronted the reality of what it means to be human in the vast emptiness of space. And now, after all of that, we arrive at the most important question of all. Why? Why do we ask this question? Why do we dream of reaching another star? Why do we sacrifice everything for the chance to explore? The answer is woven into the fabric of who we are. It is part of our nature, our restless curiosity, our need to understand, our refusal to accept limits. Our ancestors looked up at the night sky and wondered. They told stories about the stars. They named them. They used them to navigate. They dreamed of reaching them. We are no different. We still look up. We still wonder. We still dream. The only difference is that we now have the technology to turn our dreams into reality. But why? Why do we explore? Why do we push beyond the familiar? Why do we risk everything for the chance to discover something new? Perhaps it is because we are curious. Perhaps it is because we are restless. Perhaps it is because we refuse to accept that we are confined to one planet, one solar system, one corner of the galaxy. Perhaps it is because we know deep down that there is more, that the universe is vast and full of wonders we have not yet seen. that we are part of something larger than ourselves. This is the cosmic perspective, the realization that we are small, that our problems are small, that our entire existence is a flicker in the vastness of time. And yet, despite our smallness, we dream of the stars. We reach for them. We refuse to accept that we are alone. Are we alone? Is there anyone else out there, looking up at their own night sky, wondering the same things? Are there beings on distant worlds, asking the same questions, dreaming the same dreams? We do not know. We may never know. But the possibility is enough. The possibility that we are not alone. The possibility that somewhere, out there, someone is listening. That is what drives us. That is what keeps us reaching. That is what makes the journey worthwhile. The journey itself is the meaning. The act of reaching for something impossibly distant changes us, even if we never arrive. The pursuit itself is what matters. The question is more important than the answer. And that is the deeper truth, the one we have been moving toward all along. We explore because we must. We ask because we cannot help it. We dream because it is who we are. And that is enough. If you have watched up to this point, it means you enjoy these quiet, deep journeys into the cosmos. You are the reason we create this content. You are the reason we spend hours researching, writing, and refining these narratives. If this journey meant something to you, take a moment to subscribe. It is a small action, a simple click, but it means everything to us. It helps these videos reach more curious minds, and that is all we could ever ask for. Until next time, keep looking up